Okay, so activity 7C, again a video of hopefully just some tips on how to answer each question, so some hints if you like. Question 1, railway wagons, negligible friction, vertically falling rain. Rain falls into the wagon and accumulates there, so what happens to things based on momentum? By considering conservation of momentum, explain what will happen to the speed of the wagon. Ignore the effects of drops hitting the front of the wagon. So what is this rain doing? Well, let's see, the rain is falling vertically, the wagon is rolling sideways. So the rain falling into the wagon is exerting a force downwards, so we'll call it the F of the rain. But of course, does that have any effect on the velocity of the wagon? And the answer is no, because it's just resisted by the support force from the ground. So what effect does the rain have? What you need to do is think about how the rain affect the mass. Does the rain affect the momentum? So firstly, does the rain affect the momentum? And we sort of answer that with this. The force is the wrong way around. And what does it affect? So does it affect the mass? If it affects the mass, then it will affect the velocity. Because if the momentum is the same, because we've got P equals mv, so for the same momentum, if we increase the mass, the velocity must change as well. So work it from there. Part B. The rain stops, a drain plug is opened in the bottom of the rolling wagon, allowing the accumulated water to run out. Explain what will happen to the momentum and speed of the rolling wagon plus water within it. So this is looking at it in a similar thing, except that here you have to think about what's going on. So as you approach this one, think about it's not just that the mass is decreasing, because that might imply that the wagon goes faster. You need to think about what velocity and what momentum does this water falling through the wagon carry away with it. What speed, momentum does the draining water carry away? Okay. Question 2. Another game of snooker or pool, really common in momentum stuff because you're talking 2D collisions and things. So this is question 2 down the bottom of the page here. In a game of pool, the white ball is hit by the cue and travels with a momentum of 0.15 kilogram meters per second to the left towards a stationary coloured ball of mass 45 grams. The balls collide, and afterwards the white ball is travelling at 0.10 kilogram meters per second this way, and the coloured ball is travelling at right angles to the white ball in a direction that way. Always making it at right angles makes it easy to solve using trigonometry. A. Draw a vector diagram to show the total momentum of the two balls after the collision. So I think the idea here is that pool balls, these balls, snooker balls, they definitely exhibit conservation of momentum in a reasonable strike anyway. And so the idea here is that the momentum before the collision is equal to the momentum after the collision. Now what we can see is draw a vector to show the total momentum of the two balls after the collision. So momentum before the collision is equal to momentum after the collision. Well, so we can put that down here. That's the principal for equals P after, so that's the total momentum. That means that if we're asked for what the total momentum after the collision is, it's the same as it was before, so we can use that, because before we've only got the white ball, so that's easy to draw a vector. Okay, just think about what the vector for the momentum of the white ball would be. B. So the tip here was that the momentum before is the same as the momentum after, or more importantly, the momentum after is the same as the momentum before. Write a vector equation to show how the total momentum is related to the individual momentums of the two balls after the collision. Okay, so a vector equation. So it's, I guess, P total equals P white plus P red. We'll call it, I think it's a coloured ball, it doesn't really say what colour. We'll call it red for now. So P white plus P red equals P total. Is that a vector equation sufficient? I think so. I might have a quick squiz at the answer for that, just to see if that is what they were expecting you to write. It seems just a little easy. Oh, okay, they've actually substituted into this. Okay, so what they've done is they've said, okay, so the P total is this, 0.15 equals, and then they've got the P white afterwards is going this way, 0.10 plus PR. Okay, so that's what they were hoping for in that equation. A little bit more than this. So substitute the data that you have into there. C. Draw a vector diagram and use it to show that the size of the momentum of the coloured ball after the collision is 0.11. So just use this to create a vector diagram, basically. And put your numbers on here from this arrow and this arrow. And solve for PR, or the momentum of the coloured ball. Okay. Oh, there's more, but wait, there's more. D. Calculate the speed of the coloured ball after the collision. So this just uses P equals mv because you're given the mass. Note that the mass is in grams. So you're going to need to do a unit conversion, 1,000 grams to a kilogram. So make sure you use kilograms when you're putting it into this equation. Calculate the angle through which the white ball was deflected. You're going to use Sokotoa on your triangle here to solve for the angles in the triangle and use that to explain how much the white ball was deflected through. You'll have to choose which angle. Okay, so use Sokotoa to solve for the angles. Okay, question 3. A game of curling. Oh, this is quite topical because the Winter Olympics are on at the moment. So the game of curling is often played on frozen lakes or rivers, sliding large smooth rocks with handles called stones along the surface of the frozen water toward a target stone called a tee. 2 players curling on a frozen lake in central Otago. You'd be lucky to find one of those. One of the players sends her stone A, travelling with a momentum of 47 kilogram meters per second, that way, to the right, and towards her opponent's stone B, in an attempt to knock it out of the way. They collide, causing stone A to be deflected through 90 degrees. So after the collision, so it's before and after, we've got, I don't know what B's doing, it's going away somewhere, and A is now going this way at 8.6 kilogram meters per second. Okay, so A, draw a vector diagram to calculate the size of the change in the momentum of stone A. So this is a delta P equals P final minus P initial, and which is the same thing as, these are vectors, so it's the same thing as PF plus negative PI. And what we've got, here's your final vector and here's your initial vector, including their lengths, to continue and work that out. B1. Calculate the size of the momentum of the stone stone B after the collision. The size of the momentum of stone B after the collision. Okay, so if you have, again, it's the idea that the momentum before equals momentum after, and the momentum before comes from the momentum just of stone A. After the collision, you have two stones here, and you are given the momentum of one of them and the momentum between them. So after PA plus PB as vectors equals P after the vector. So if we know P before, which was the same momentum that the stone had before, we know this one because we know that that was also P after. So this equals that, and we have been given the momentum of stone A after. So this should allow us to do a vector diagram and solve for the momentum of stone B after. And we know that two of these are at right angles, so it's a right angle triangle, and we've just got to determine that. So, you know, it's going to end up with a diagram looks something like 47, because that's P after. PB equals P after minus PA, but that doesn't really matter at the moment, I think. This was the before, the afters have to add up to that, so PA is this way, PB is that way, and there's a right angle here because this was A travelling that way before, and afterwards it's travelling this way. So the P after equals PA plus PB, which is true. From here to here, from here to here, from here to here is the same as from here to here. And then we can use Pythagoras to solve for this, for the magnitude of PV. B2, explain any assumptions you've made. So the usual assumption here is no external forces. So that, and the reason for that, if you have external forces, then you have a change in momentum being caused by something else, which means that momentum is not conserved. C. Draw a labelled arrow on a vector diagram to show the direction of the momentum of stone B after the collision. I assume that's the assumption that they're looking for here. You can always check in the answers. C. Draw a labelled arrow on a vector diagram to show the direction of the momentum of stone B after collision. Well, if you've done your vector diagram here to know what you're doing, then you've already done this. So C, B1. After the collision, stone A goes on to hit the T. After this collision, stone A and the T are travelling at right angles to each other. The T, with a momentum of 4.2 kilogram meters per second, calculate the angle through which stone A is deviated by the collision with the T. So D is like a completely new question. You just start with A having this this momentum, and then you have, so downwards at 8.6, and then you have the T. Now, do we know what we haven't been given the masses or anything, it doesn't seem. So after the collision, stone A and the T are travelling at right angles to each other, so it comes down and hits a T, and they then end up as before, and after they end up at right angles to each other, who knows exactly how. Something like this, perhaps. Oops. Going this way, and the t going that way, and they're at right angles to each other. That's a really bad diagram, Logan. Let's try that again. After the stone A is going that way, the T is going that way, and these are at right angles to each other. And we're told that the T has a momentum of 4.2. Now the important thing here is to be able to redraw your vector diagram. T, the momentum of the T plus the momentum of the stone equals the total, 8.6, okay, 4.2, and so you'll be able to find the momentum of the stone using this, but most importantly you haven't been asked for that, you've been asked for the angle through which the stone is deviated. Use SOHCAHTOA, and what you need to do is find an angle through which it's been deviated, which is actually this angle here. That angle there is the same as that angle there, using angles, parallel lines. Was it opposite angles when you've got a line intersecting parallel lines? Opposite angles are equal. So this angle and that angle are the same, and it's that you're solving for. And you've got a side length and another side length. So you've got two side lengths. This is the opposite, and this is the hypotenuse. So you're going to use SAW, I think, to work out that angle. Okay, complex, hey? Particularly when you draw bad drawings. So look at the next question. Question 4. Well, looks like there's only 2 questions to go in this exercise. At a bowling alley, a 6.8 kilogram bowling ball travelling this way with a momentum of 44 kilogram meters per second hits a stationary pin of mass 3.5. So we've got ball that way hits a pin. After the collision, the bowling ball and the pin are moving at right angles to each other again. Always at right angles. Do you know why? Because it makes life workable. So they're travelling at right angles to each other afterwards, the ball and the pin. Actually, I should have drawn a before and after, actually. So before, after. It's worth sketching up diagrams as you go, if you can. Before and after the collision, the bowling ball and the pin are moving at right angles to each other. The bowling ball at 5.4 meters per second. And this way, yep, and the pin in that direction. And the pin weighs, rather has a mass of 3.5 kilograms. So they're giving you kind of oddball collections of information now. 6.8 kgs. So you can work out a range of different things from this. I see we've got a momentum and a mass of this one, so we have a velocity, but we don't really need that at the moment. But we have here a velocity for the ball afterwards, and we have its mass, so we can work out a momentum. We had a momentum before and a momentum after. That have to be overall the same, so we can make a momentum vector diagram. Calculate the momentum of the bowling ball after the collision, so that's part A. So it's going to break these steps down. You can sort of see from the situation that you could just take these steps yourself to kind of go through and get as much information as you can, but instead they're going to make you break it down and do it bit by bit, which is good. It leads you through it. So the momentum of the bowling ball after the collision, you're going to use P equals mv, and as I've said, the information for that is given in the question, the mass of the ball, the velocity afterwards. B. Draw a vector to show the size and direction of the total momentum of the bowling ball and the pin after the collision. So this is using the idea that P before equals P after. Now, which thing is moving before? Only the ball, and therefore it's only the momentum of the ball you need to deal with before, and you're given that as one simple thing, so just draw that vector with its and give its size. C. Show that the size of the momentum of the pin after the collision is 24 kilogram meters per second. So here you've got a vector diagram. If this was the momentum before, then it's afterwards, it's also the momentum after, and it's got to be made up of the momentum of the pin and the momentum of the ball, which you've just calculated. The P of the pin, not just the pin. The P of the pin and the P of the ball have to add up in Pythagorean sense to 44, and you know the P of the ball from part A. Okay, D. Calculate the angle through which the bowling ball was deviated by the collision. So the bowling ball was going this way and is now going that way. So again, we're looking for this angle here. That's the angle of deviation. It was going this way, now it's going that way. And so, let's just redraw that. So here's your vector diagram. And so it was going this way. It was going this way, which is parallel to our momentum before or momentum after. And it's now going this way. So it's this angle here, which is the same as this angle here. So if we have all the various side lengths, we can solve for that angle there using SOHCAHTOA. Part E, explain the size, or why the size of the change in momentum of the bowling ball is the same as the answer to C. So this idea is really Newton's third law that combined with, perhaps combined if you wanted to, with delta P equals Ft. Okay, so keep in mind here what Newton's third law is that for every force there is a equal and opposite reaction force, and so when two things collide, one of those things sees a force in one direction, the other one sees a force in the equal size but in the opposite direction, and of course those forces must also last for the same amount of time, so the magnitude of the momentum change is the same, and the only thing different between the momentum changes is that they're in opposite directions. So try an explanation along those lines. If the bowling ball and the pin are in contact with each other for 0.09 seconds, calculate the average size of the force of the bowling ball on the pin. So here you need to do a change in momentum calculation. Now, as it's pointed out, the change in momentum of the pin is sufficient to work out that calculation. The pin had no momentum before, so as long as you don't need the momentum, know the momentum after, then you're good to go. So work out the if we hadn't worked out the momentum of the pin yet, yeah, show that the size of the momentum of the pin after the collision is 24. So you can just use that, and delta P equals F delta T, and the momentum given for the pin, and that will give you your answer. Alright, question 5, got one more to go. Just turn that around, do this here, hopefully I can still fit this on the page. Question 5, a rock with a mass of 31.6 kilograms is precariously balanced on top of a cliff and is in danger of falling. It is decided to blast the rock apart with explosive. The explosion causes the rock to break into 3 pieces, each travelling in a horizontal direction. Cool, so the rock's going to go but horizontally. Piece A, oh no, it's not. We're looking at it map-wise. So top view, let's just draw it. So piece A is travelling north .95 kgs and is travelling north at 6.75 meters per second. B is travelling west at, well, B has got a mass of 11.6 kilograms, and is travelling west at 5.55 meters per second. And C has got a mass of, not given, kilograms, but though we are given that those total 31.6 kilograms. So we can figure out, we can calculate the mass C. I think you should be able to do that without any further assistance. And then what we need here is we've got C, and where is it going? Well, if those are going that way, then this one's probably going this way, because overall we've got conservation of momentum. Okay, an explosion situation basically says we're applying an internal force to blow this rock apart, which means that all the parts must travel away from each other in a way which means that the momentum after is the same as the momentum before. Now, the momentum before was a stationary rock, so the momentum after must be the same as that, which is essentially zero. So the net momentum, if you like, or P before equals P after equals 0. So PA plus PB plus PC equals 0. This is the vector kind of equation, and that means that you should be able to do a vector diagram. PA, remember nose to tail addition, PB, and PC has to get back to the same point. Okay, now we're told that this is north and that's west, so this is 90 degrees. We can work out the momentum A from MA times VA. We can work out momentum B, MB times VB. And once we've got momentum C using Pythagoras' theorem in our triangle here, we've got momentum C equals, and we can work out the mass C here, mass C times VC, and we can get the speed of the third piece, which is what we've been asked to do. To calculate the direction of the third piece, we need to work out one of these two angles and use SOHCAHTOA. So part 1, we're going to use that, and part A, we're going to use that, and part B, we're going to use SOHCAHTOA. SOHCAHTOA. So we're going to use our trigonometry to work out an angle. Okay, so hopefully those are some helpful tips for how to complete exercise 7C.